And I was thinking I'd structure the talk in two parts. The first part is focusing on what we will call the sharp regression discontinuity design, and we'll make a couple of examples, and then we hopefully also have time to talk about the so-called fuzzy regression discontinuity design, which nicely ties with the things that Vanessa already mentioned, so I could just, sort of stand on the shoulder of giants here and show you how even with sort of an imperfect jump from control to treatment, we can use this design to make causal inferences. And I understand that the regression discontinuity design has become very much en vogue in many social and economic sciences over the last couple of years, which is always a little bit surprising because it's not a new idea at all. Fistelwade and Campbell came up with this idea in 1960, but unfortunately many people, including me, don't really read out of our narrow disciplinary boundaries. And then it took really a couple of decades until that caught on and people understood that this is, despite the very particular design that we need, a very useful thing that we can apply more often than we think. And I try to convince you of that during the next 40 minutes. So the basic idea is the following, that as often in observational, i.e. non-randomized studies, assignment to treatment and control is not random, right? But what we know in order for the RDD to work is the assignment rule that influences how people are assigned or selected into treatment or control. It's surprisingly widely applicable in a rule-based world, and I'll give you a couple of examples later on. And under fairly weak assumptions, it has high internal validity. So it's one of the few methods that in replication studies has been showing to identify the actual causal effect in a non-biased way that we would like to estimate, and I'll say more about that in a second. So here's the outline. We first talk about the sharp regression discontinuity design, then go on to the fuzzy regression discontinuity design. At the very end, I have one more slide of like further issues, right? Things to explore in the future. So just very briefly about identification. This is super simple, so we can do that quickly. Imagine we have a binary treatment to make our life as simple as possible. Taking on value 1 if on x, which is what we call the forcing variable, if we exceed a certain threshold c, and value 0 below. And I'll make an example in a second. Okay? So x is not just like a covariate here, but a very particular forcing variable that determines the value of your treatment, right? And these types of design often arise from administrative decisions. So let's look at an example in the spirit of the original example by Fistelwade and Campbell here. So let's assume you're a university and you hand out scholarships, right? And you do so because you want to make your life simple on one single score. So let's call it the SAT score, if you will. And let's say for students who exceed a value of 2,000 on that score, they receive the scholarship, but nobody below 2,000, right? And so we have this discontinuity in the probability of receiving the treatment at 2,000, right? And the basic idea for the RDD, and basically, thing that I'm going to talk about for the next 40 minutes, is that we compare people close to that threshold of 2,000, right? Those who just barely exceed the threshold and receive the scholarship, to those that barely miss the threshold and don't receive the scholarship. And that's all there is, right? So at, the threshold of 2,000, we have this discontinuous jump in the probability of receiving the treatment from 0 to 1, right? And whatever the outcome that we're interested in here, for example, it's earnings, a couple of years after these students obtained their university degree, what we might see then is also a jump in the outcome variable, right? And clearly, the SAT score down here is correlated with earnings. Students who have higher SAT scores are typically better at making a lot of money afterwards, right? And so the basic idea is that we focus our attention on those who barely receive a scholarship to those who barely missed it, right? And basically that jump in the observed outcomes at the threshold is then the causal effect of receiving a scholarship. So we can do that in the potential outcomes framework, but we don't have to use the potential outcomes framework. But the basic assumption here we can nicely illustrate in the potential outcomes framework. So what we observe for the people just below the threshold is the outcome without the scholarship, the blue line, right? What we observe for the people who received the scholarship above 2,000 is the observed outcome, that is income, with the scholarship. And what we want to estimate is this local average treatment effect here. And I do understand that in the instrumental variables framework that Vanessa was talking about, people are also using local in order to refer to the compliers, right? But what I mean here is local for the people close to the threshold, so close to 5 here or 2,000 in our SAT score example, right? So in that sense, I mean local. And the only assumption that we have to make, I'll say more about that in a second, is that the two potential outcomes, both under treatment and under control, are smooth or continuous at the threshold. And if that's the case, the only task left, and I'll simplify here a little bit, but the only task left is that we model, in a decent way, the point here of the potential outcome under control just below the threshold and just above the threshold, right? So in that sense, it's a prediction problem to the cutoff. Okay, so let's talk about identification for a second. There's, when looking at the literature, sometimes a little bit of confusion, because a lot of people say that in the vicinity of the threshold, treatment is as good as randomly assigned. And to be honest, I'll make those statements as well. But that doesn't really say us, I think it's nice for intuition, but it doesn't tell us much about what we actually need to identify the effect. The only thing we need to identify the local average treatment effect is the continuity of the two potential outcomes under treatment and under control at the threshold. Obviously, we'll never ever be able to test this because we don't observe the potential outcome on the treatment for those below the threshold and vice versa for the control units above the threshold. But there are fortunately indirect tests, and D-smoothness is the only condition that we actually need. Okay. If that condition holds, we can approximate the causal effect, that is the treatment effect for the sharp regression discontinuity design, by approximating the potential outcome under control from below and the potential outcome under treatment from above. And right there at the threshold, this is treatment effect that we would like to assess. Okay, so let's talk about two brief examples here. First one goes back to David Lee, an economist who sort of came into political science and answered one of the bigger questions that people in political science has, and it's a question about the so-called incumbency advantage. So if you're already holding office and you're re-running, are your chances of ending up in office again, winning the election, higher than for someone who newly comes in, right? There might be many reasons for this, because people know you already, there's less uncertainty, maybe because you can use the power of your office in order to convince people one way or another to vote for you in the next election. So this is not about the mechanism, but just the overall effect, right? And this is not easy to identify empirically, because obviously better candidates who are able to win the first election, there might still be good candidates more likely to win the second election as well, right? And so what David Lee did is, instead of focusing on the personal, individual level incumbency advantage, looked at the party incumbency advantage. And here he compared, this is the Vulture Margin, so if it's positive, that means that the Democrats have won, the Republicans if it's negative. And what we see here is that if the Democrats have won narrowly in the election at time t, then they have about a 7% higher chance of winning the election at the next election t plus 1, right? And so this difference here then is what we could identify as the local incumbency advantage. Okay. There might be also other ways to use the regression discontinuity to design, and I understand the next speaker will talk about the temporal RDD, so I'll focus here just on the spatial RDD, basically exploiting geography so that we can also learn something about things that discontinually change at some borders, right? And what we see here is based on a paper by Melissa Dell, which was then published in 2010, where she was looking at the effect of the META, basically, form of slavery system that forced people affected by that system to send, or the villages affected by this system to send every seventh son to work in the mercury or silver mine in Peru in the 18th century, right? And so what you can do, because there are these discontinuous borders that only villages within the border had to send their sons slavery system, but not the villages that were just outside of this border, we can use the border as sort of the threshold here, right? And what Melissa did in her nice paper is that she looked at some outcomes today, like equivalent consumption and childhood stunting, and found some big differences for those villages close to the border, just within, compared to those just outside of that border. Right? Clearly, one thing that is more problematic or something to worry about when you use the spatial regression discontinuity design compared, say, to the SAT score from before is that you have to be absolutely sure that there's nothing else changing at that threshold other than this meta-conscription system, right? And so, for example, I grew up in a nice small city in Switzerland, Fribourg, where there is a river dividing the German and Swiss-German French-speaking parts, right? And I always thought, well, maybe we can use this discontinuity in the language to study something interesting. But of course, the issue is that many things change once you cross that river, right? People are reading different types of newspaper, eating different types of food, so you're not really know what you're estimating when you're focusing on this border. So this is not just in this example from my hometown, but often an issue. So you really have to argue, that everything else, then the thing that you want to study is actually constant at that point. So, let me talk a little bit about estimation. And unfortunately, it's something that we don't know very much about in the context of RDD. What we know, and what is simple, is of course that we somehow want to approximate, as I said, this threshold from below and above. And I can do that with a linear model. I can do it with a quadratic or with a cubic model, or higher polynomials, if I will. What is more important, however, is the question of which bandwidth, which window size shall I pick to the right and to the left of the threshold, right? And obviously, the larger window, that it gives us more precision, but also more bias, right? So it's a typical variance bias trade-off, and depending on how you, what you believe more important, that has implications in how you pick that window. So there is a little bit of literature and 3 suggestions how to do that. The first one is based on cross-validation by Ludwig and Miller, 2007, in a nice article. But what we know from one validation study that I'll talk more about in a second, and most of simulation studies, that doesn't work very well in most cases. Then there is the nice Invens and Hangartner bandwidth selection, which is sort of mean squared error optimal under some assumptions, right? And that has been shown to work in some contexts quite well, but not in others. I'll say more about that in a second. And lastly, this is a new paper by Kalonika and Matthias Gattanetto and Rocio Tikunik, which is a nice paper where they sort of try to find a bias correction method in order to recover the unbiased data, right? And so these are 3 different methods. We don't really know which one works best. Yes, please.
Sorry, I've missed what the bandwidth is. Can you just go back and
sorry for that. So the basic question is, how much of the data to the left and to the right, the window doesn't have to be the same size, do you want to use, right? In approximating this point here and this point here, right? The larger the window, more data you're using, higher precision, but also larger bias, right? So the basic question is, how shall I pick the optimal window size? What's that?
I'm confused why you'd ever not want to use all of the data.
Well, because if you're using much more data, that could lead to some, and you just say with linear regression through here, you could have some bias here. You're not really interested in, modeling the data over here very well. The only point of interest is here right at the threshold, right? And so that's why it's a little different than, some other specification searches. Okay, so let me talk a little bit about these 3 methods. And again, as I said, we don't know very well, in an actual context, which one works best. Obviously, we can come up with simulation studies, but with simulation studies, you can prove pretty much whatever you like, right? Give me 3 parameters, I'll build you an elephant. Give me 4, I'll make him dance, right? So, a very nice paper by 5 Finnish friends of mine, so I will not pronounce their names. Heaton and et al. It's a working paper, just been rejected for reasons I don't understand. Is the following. What they do is they focus on a case where we know the experimental benchmark. So it's like the Lalonde 1986 study in spirit, but for regression discontinuity designs, right? what do? They focus on the incumbency advantage that I introduced before. But in Finnish local elections, it's proportional representations, and parties have different lists of candidates, right? And you vote for the different candidates on the list. And because, Finland is not a large country, and they have many municipalities, quite often, on the same party list, two candidates have the same number of votes, right? So what happens? Well, what happens is that they put the name into a hat. I'm not making this up. Into a hat, and then they draw, the winner out of the hat, and this person then gets in office, and the other person doesn't, right? So this really are random elections, right? And I think this is interesting to study in its own right, but it's also great to try to validate the regression discontinuity design, right? Okay. And so this is sort of in the random election, the incumbency advantage that we see. It's basically a fairly precisely estimated zero, right? Independent of the specification, right? Now, the issue, once you try to model that data, is that there's quite a bit of curvature around the threshold, right? So this refers back to your question from before, right? If I use a linear specification, it's hard to see in the back, but basically we estimate a treatment effect which is the difference between this point and this point, right? So clearly non-negative, right? Then if you use a smoother specification, quadratic or cubic, what we see is that the treatment effect goes to zero, right? And so, which is then obviously consistent with the experimental benchmark here, right? So we clearly see that, the way how we model that might, give us a wrong estimate or not. And so then what we can do is use the three different methods, Ludwig-Miller cross-validations, IK, MSE optimal, and then the CCT bias correction to see which one performs best in this particular context, right? It's just one data point, of course, right? But at least it's a start, okay? And so unfortunately, the basic answer of my take on the results is the following, that except for the CCT bias correction, none of these methods actually work very well, unless, and that's the good news, you do some undersmoothing, right? So if you choose a window size according to I and K that's optimal for a linear model, you get a biased estimate. You find that, in other words, significant incumbency advantage, right? Because you get the curvature wrong. But if within that bandwidth choice, optimal for the linear model, you actually fit a quadratic or a polynomial model, you do some undersmoothing, then you get back to the experimental benchmark. But fairly precisely estimated zero treatment effect, right? So my take-home point at the moment from that is that either you do the bias correction, you have to make some assumptions here as well, or you do some degree, at least one order, of undersmoothing. And again, it's just one data point, but that's what we know. All right? Okay. So, fortunately, there are more things that you can do. As I said before, we are never able to directly test the smoothness assumption at the threshold, right? We do not observe the potential outcome under control for the treated units and vice versa, right? But there are, of course, many implications, indirect tests of that assumption. And, I think the strength of the RDD is that it allows us to do these indirect tests, okay? So here's just an overview. First thing I think that's useful to do is the sensitivity, similar to what we just discussed, right? Do you get very different results if you use one more polynomial, right? Second thing that you can do is, with the specification that you've chosen for the outcome, you can also look at some covariates not affected by the treatment. And what you don't want to find is similar jumps in those pseudo outcomes there as well, right? The third thing that you can do is that, okay, there should be a treatment effect at the threshold, but there should be zero treatment effects, if you move pseudo threshold to the left and to the right? And of course, if you find similar jumps, like -5 or +5, that also casts some doubt about, the treatment effect that you find at zero, and maybe then it's just because of, that you didn't really capture the curvature of the regression lines. And the last, I think, very important test is sorting, right? And I sort of, skipped over that a little bit in the intro, because what we are assuming when we are saying that the sort of smooth at the threshold, one sort of behavioral implication of that is that the units of the analysis don't have discrete control of landing to the right or to the left of the threshold. Obviously, if I learn more, invest more in preparing for the SAT score, I can push, hopefully my scores, up. But I don't have discrete control that, if I invest like 10 minutes more, I go from 1,999 points to 2,000, right? So what we have to assume basically, behaviorally, is the units of analysis don't have discrete control of if they want to be to the left and to the right, or to the right of the threshold. So I hope you don't mind, but one case that I looked into and tried to analyze and then had to stop is looking at the effect of higher salaries for Italian mayors, right? Because the maximum cap of salaries for Italian mayors changes discontinuously at some population thresholds. So if you have 3,500 residents, then your maximum salary is 40% higher than the 3,499. Now, if you look at the density, of the number of people living in those villages, not surprisingly, you see a sizable jump, right? You have many more villages with just 3,500 than 3,499. Of course, what you do is, you call your brother and offer them some money to move to your village, right? And everybody is better off. Fortunately, that has testable implications, right? Because without sorting, we would see no discontinuous jump in the density at the threshold, right? And if we are, so this is sort of the opposite of the Italian mayor example, if we have unemployment benefits, for people below a certain income, right? Now they might make sure that, they just don't reach the threshold, and so we have more people just below than just above the threshold, right? But obviously there are different tests that you can do, including the McCrary test from 2008. All right, let's move on to the fuzzy regression discontinuity. Right? So the difference between the sharp and fuzzy RDD is very simple. The basic difference is the following: that you have a forcing variable like before SAT scores, and you have a threshold like before 2,000. But the probability of receiving the scholarship doesn't jump from 0 to 1, but say from 30 to 70%, because you're not as lazy as I would be and just look at the SAT score, but you also look at, say, letters of recommendation, right? Or curricular activities of the students, right? So there is a discontinuous jump at the threshold, but it's not one from 0 to 1, right? And so in that sense, it will relate back to what Vanessa talked about, where we use the discontinuity, the threshold, as an instrument, okay? So this is the thing that I'd like to talk about for now. So what we shouldn't do with this, in this fuzzy RDD world, is just compare recipients with non-recipients, even close to the threshold, right? Because let's say you're focusing on two people above the threshold, that's 2001, right? One of them received the scholarship, the other didn't. Well, clearly there's some difference between them, right? Maybe the letters of recommendation were better for the first than the second one, right? So you shouldn't just make that comparison. But what you want to do is that you want to focus on the compliers. Compliers in this framework is a student who switches from non-recipient to recipient of the scholarship when crossing the threshold, right? That's a complier in this context. But you don't want to focus on people who get the scholarship anyway, independent of if they are just below or just above. These are the always takers, or the never takers, who would be the people who wouldn't get the scholarship even if above the threshold. Right? Okay, so this is sort of the graphical interpretation of the same thing, right? So what we see here is that we have an increasing probability in receiving the scholarship if your SAT scores goes up. But in addition to that, important for our purposes, we have a discontinuous jump in the probability, basically from 40 to 60%, right? And so we are using that now as an instrument. We can similarly define the local average treatment effect. This is the differences in observed outcome, which is not the same as the difference in the potential outcomes. Why? Because we have to scale it by the proportion of people that only receive the scholarship if they move from below to above. That is the proportion of compliers. Right? Okay. In terms of identification assumptions, fortunately, I can mention what Vanessa already said earlier today. So you need a binary instrument. You restrict your sample only to those close to the threshold, and the optimal window is again something that we will have to discuss. And you need to invoke the usual IB assumptions, right? So ignorability, first stage monotonicity, all the things that you already mentioned in your talk. If these assumptions hold, then what we can do is that we can identify the causal effect, very local now. It's the effect at the threshold for the compliers, right? Between the two potential outcomes by, on the one hand, approximating the differences in the observed outcomes divided by the differences in the probability of receiving the treatment, right? Or in other words, you divide, it's the Wald estimator here, is the outcome discontinuity by the treatment discontinuity. Okay? And the way to do this is you use the simple Wald estimator, fit a two-stage least squares regression. You can add polynomials to do a little more flexible specification, but again, with some debate is, what's the optimal bandwidth that you want to go to the left and to the right. And I also think it's usually very helpful to separately plot the estimates of the outcome and the treatment discontinuity. Okay, so let's make an example. And it's an example from my own research where I've been interested for quite a while in the effect of citizenship on immigrant integration. And the policy debate, and I don't want to bore you with the details, but it's basically, on the one hand, those who argue that we should give citizenship to people fairly early on. So not having too high of residency criteria, because receiving the host country's passport catalyzes in a causal way the integration of immigrants, right? And you have, on the other hand, in the Swiss context, that's the Swiss People's Party, who will make a very different argument and say, no, if you hand out the Swiss passport too early, you destroy all incentives for these people to integrate, right? Because receiving the passport in itself has very little effect, if any, right? But it's sort of the bonus you get at the end of a successful integration, right? And obviously, if that hypothesis is true, then there's very little reason to handing out, the passport early on in the residency period. But what we should do is making it very difficult for people to receive the passport, right? Okay, so to study that empirically is unfortunately not trivial, right? It's very obvious that it would involve some comparison of naturalized to non-naturalized immigrants. But once we think about it, it becomes clear that there's sort of what we call double selection bias going on, right? On the one hand, we have many applicants, unfortunately here in black, I shall change that, who don't have the motivation, don't have the resources to apply for citizenship, right? Maybe they don't fulfill the eligibility criteria, right? On the other hand, in red here, we have people who have the motivation, resources to apply, but at some point during the application process or the screening interview, they are screened out and rejected for citizenship, right? And in many countries this happens quite often. And lastly, we have the people in green who have the motivation, resources to apply and to successfully navigate the application procedure. And so a comparison between the naturalized and non-naturalized would really be sort of the apple-orange comparisons that we don't want to make, because a lot of these factors that are different between the naturalized and non-naturalized are also influencing, integration down the line. Okay, so fortunately what we can do is that we focus on a strange institution in Switzerland where people in municipalities, voters, vote on each individual citizenship request. Okay? And so we focus on those who just barely win and barely lose this election. How does that work? So it's basically 4 to 6 weeks prior to the vote, a resume with the applicant characteristics is sent out to all voters in those municipalities. And it's very detailed here. It's in Swiss German, but we have this woman from southern Italy, from Sicily. We know when she was born, her marital status, her employment history, her education. And we know when she moved to Switzerland and into this particular municipality. And lastly, we have some stylized facts from her last tax record, including income and wealth. Right? And so with that information at your disposal, then people vote yes or no on these naturalization requests, and if you have 50% or more of the yes votes, you immediately receive citizenship, and if you have 49% or less, you don't, right? And so clearly what we want to do is focus on those who barely win or barely lose these elections. Okay, so what we had to do is that we had to figure out which municipalities use that system of voting on naturalizations, extracted the resumes from the municipal archives, then based on these resumes we have people's address and name back then, and then about 15 years later we called them up and subjected them to an interview to assess their social and political integration, right? And there's one reason why this is a fuzzy regression discontinuity design, and the reason is that you can reapply if you reject it, right? And some of you might like to hear that in 2003 the Swiss Supreme Court stepped in and decided that these types of naturalization referendums are unconstitutional, right? For, fairly obvious reasons, risk of discrimination, and so on and so forth. They had to change the system, and under the new system it was much easier to apply. Meaning, a lot of the people who were barely rejected reapplied at the time of the interview successfully for citizenship, right? So among those who in their first assessment, in the first application had just 50%, the zero here, right? 50% yes votes, all of them obviously still have the Swiss passport, right? But even among those who were barely rejected, by the time of the interview, about 2/3 already have Swiss citizenship. So this is a fairly fuzzy regression discontinuity design, and what we are using here is the threshold as the instrument, right? And because it's one-sided non-compliance, right, on the non-compliance on this side, it also means that the local average treatment effect that we're estimating here has one particular interpretation that goes back to the Bloom result in 1984. It's the average treatment effect for the untreated. So how much would these guys here do better if they would have been given the Swiss passport in the first naturalization referendum? Okay? And so I will not bother you with the details about how we measure social integration, and obviously that's a big debate, but we ask them questions like, do you plan to stay in Switzerland, or do you think once you're retired you go back to Italy or Turkey or wherever? Do you feel like you're discriminated against, right? Are you parts of social clubs? How many, right? Are you reading like Swiss newspapers or exclusively Turkish newspapers? So a battery of questions, and then we did principal component analysis and extracted the first principal component from that. And so this is the intention to treat effect on the outcome. And what we see here is that the variance in this so-called this constructed social integration scale is about 0.5. So we see a sizable jump here. This doesn't say much about the statistical significance in the social integration for those who were barely accepted in the first referendum compared to those that were barely rejected, right? And we have to scale up this difference, of course, by the proportion of compliers that I've showed you before here, the 0.3, right? So that we see that if you do that calculation, we see that people who were barely rejected in their first naturalization referendum, if accepted, would perform better on the social integration scale by about 1 standard deviation, right? 15 years later. All right. So, very briefly, further issues. I think in addition to the bandwidth choice, the big open question is if we can do a little better in terms of external validity than just saying this is a very local average treatment effect right at the threshold, right? Clearly, if we want to extrapolate away from the threshold, we will have to make additional assumptions, right? So that's very clear. And there's been a little bit of research recently by Angrist and his PhD student. It's still unpublished as of now, but they basically use covariate information to inform us a little bit about how strong the assumption need to be in order to extrapolate away from the threshold, right? And so hopefully, with some better methods and a little bit more covariate information, we can not only learn something about the people right here at the threshold, but also the people, that are a little bit to the left and a little bit to the right. So that's not just this dichotomous high internal but extremely low external validity. Thank you so much.
I have a question. So you nicely emphasized the smoothness assumption.
Yeah.
And I was wondering whether there are situations where the threshold is actually there for a reason, because maybe in a medical context or so, because they think it's not smooth. People really benefit more of treatment if they're this side than that side.
Yeah, and
So
that would.
how would that be a problem?
Yes, so it depends, but I think one way to think about that is people just above the threshold are doing much worse than people just below the threshold, right? That's sort of the underlying idea. And then obviously the potential outcomes are not smooth, right? Because with or without treatment, you would expect a drop in quality of life or whatever you're measuring right there at the threshold, right? So that would be a violation of the smoothness or continuity assumption.
Are people trying to detect that, or is there somewhere?
Yes. So there are some methods that now sort of get more and more fancy, but that doesn't mean that they are new, right? Which try to answer a related question to yours, namely, if there are these threshold effects, but we don't know where they are exactly, right? Can we detect them, right? And so, of course, things like reversible jump MCMC and all these other algorithms, which are good at these tasks, could be used for that, right? And one of my paper, which I think is very nice, studies white flight in the US. So basically, white people who at a certain point, there's a lot of immigration from African Americans, start moving away, right? And so what they try to find is these sort of thresholds, when there's white flight is happening, right? And this is sort of an RDD, but with unknown thresholds, right? And so the task is, of course, that we have at the same time to estimate where is the location of the discontinuity and what is the size of the chunk.